Hello, everyone. Thanks for joining our seminar. I am Yan Rong, the student chapter chair. It is my great pleasure to introduce our speaker today. We are very excited to welcome Dr. Alex Sun with us. Alex is currently a postdoc in mechanical and aerospace engineering at the University of California, Irvine, where he worked with Professor Ramin Bostanabad. Alex's research focuses on the intersection of physics-informed machine learning, computational mechanics, and design optimization. In particular, he focuses on developing more efficient and interpretable approach to topology optimizations. Before joining UCI, Alex works as a research scientist at Collins, and also spent time as a postdoc at the University of Wisconsin-Madison. He earned his PhD in mechanical engineering from Johns Hopkins University. Alex's research includes scientific machine learning, multi-physics design, and experimental mechanics under extreme loading conditions. His long-term research goal is to build AI-enabled frameworks that connects experiments and computational tools with the aim of design materials and structural systems that perform reliably in extreme environments, especially for aerospace and defense applications. We are very glad to have him to give a talk today. Let's give a warm welcome to Alex. Now the screen is yours. I will mute myself.
Okay, thank you, Yanrong, for your introduction, and I will share my screen. Let's get started. Thank you very much for attending my presentation at this time. And yeah, so today I'm going to talk about physics-informed Gaussian process to do topology optimization under some advanced topics such as multi-material and multi-physics. And also, this is my postdoc work at UC Irvine. So in this work, I collaborate with my colleagues, Ami and Sharon, in the Department of the Mechanical Engineering under the supervision by Professor Ramin Basnabad. Before I dig into the details of my presentation, I want to briefly talk about my research vision. I have a PhD study focusing on the experimental mechanics at a very high strain rate using experiments such as pressure shift plate impact, where we studied the multi-axial high strain rate loading on ceramics and metals. And also I use techniques such as DIC, digital image correlation, to capture the heterogeneous deformation in full field. As we all know that these dynamic experiments can be super expensive to implement and also very time consuming. Also, more importantly, those domain knowledge about the materials mechanics is not readily available for application purposes, such as structural design. So motivated by this gap, I want to build my future research based on machine learning in three major thrusts. First, I want to accelerate the experimental characterization using machine learning, such as building the digital twin models, and we can use this digital twin to calibrate the materials parameter simultaneously with the experimental characterizations. Second, I want to build like physics informed circuit modeling using the machine learning, where we can cover a wide range of material libraries, and also we can simulate the complex physical process with high fidelities. The ultimate goal of my research is to really put all this knowledge of material and also experimental mechanics into the design purpose and applications. So I call this a physical-driven material and structural design. And today I'm going to show you a very preliminary design framework based on machine learning for topology optimizations. Okay, so here is the outline of my presentation. First, I will briefly talk about physics-informed machine learning and also topology optimization, just give you some detailed backgrounds. And then I will introduce our physics-informed Gaussian process framework for the compliance minimization, which is a benchmark topology optimization problem. Our framework is mesh-free and also based on the Gaussian process. So our Gaussian process uses the neural network as the main function, which is very powerful to model quite complex stress localizations, for example. And then furtherly, I will extend this I will further extend this compliance minimization framework to more advanced topics such as multi-material and multi-physics topology optimization. In that extended framework, we will handle both the adjoint problem and the non-self-adjoint problem. And finally, I will demonstrate our capability using a multi-physics example, such as the thermomechanical device design. Okay, so machine learning is a set of powerful tools for modeling complex systems. So depending on the availability of the data, machine learning can be a data-driven approach and also can be no data or very little data. So in that no data case, we call it the physics-informed machine learning. It's just like the scientific computing technique, such as the finite element method, where we can model a complex physics system or to get the solutions of our complex governing PDE. So topology optimization, is a good topic at the intersection between the computational mechanics, machine learning, and the design. It draws a significant attention in engineering design applications, such as the Minecraft design, also the design for the helmet for protection purposes. So topology optimization is a method to determine the material distribution by minimizing a specific objective functions. So those optimization is under the constraint by several physics, for example, by the PDE constraints and also the constraints from the volume fraction. Classic methods such as solid isotropic material with penalty has been pretty much well developed, right? So this simple method use a design variable of the density, which ranging from 0 and 1, with 0 corresponding to the void and 1 corresponding to the solid. This method has been very well developed in recent years, and there are some advanced topics around multi-scale, multi-material, and multi-physics. And most recently, people use nonlinear materials constitutive response, such as plasticity, to do topology optimizations. However, there are very limited amount of work that explore machine learning's application in this advanced topics. Today, I will be focusing on multi-material and multi-physics as the advanced TO problems. However, machine learning has already been quite used in topology optimization regime. So this work here present the supervised approach, where they train this neural network to predict the sensitivity map. This supervised approach can accelerate the compliance minimization by 10 times for very large scale problem, like 10 or 120 million elements. So if we do not have data and we can use physics-informed machine learning for topology optimization, those four papers combine the physics-informed machine learning with like a finite element and also combine the machine learning with a deep energy method to do TO. However, all those approaches have a similar algorithm structure where for each density update, you have to solve for the displacement or solve for the solution variable. So this is a structure we call it a nest structure, and it can cause pretty high computational costs, especially using machine learning or physics-informed machine learning solver to get the solution variables. So as I just mentioned earlier, right? So the existing machine learning method for TO has many issues. It can be very expensive to compute, and it has very slow convergence to false balance conditions. And also, at the beginning of the training, the accuracy is pretty low, right? Because we are minimizing the residue of our PDE system, and also we are minimizing the boundary conditions, which may not be satisfied. So one question we can ask is, can we accelerate the convergence while also keep a high accuracy? Yes, the answer is yes. And I'm going to show you how we are going to do the compliance minimization, which is the benchmark TO problem, through our framework called the physics-informed Gaussian process. So this slide shows the general comparison of our approach with the classic TO approach, such as the SIMP. So our approach is a simultaneous and mesh-free approach, where by simultaneous, I mean we optimize the topology, such as update the density field simultaneously with solving for the state variable. Here is a comparison. For a classic SIMP method, you can see we solve for the displacement or solve for the solutions iteratively for each density update. What we believe that this nested solution step is unnecessary. What we do is for each iteration step, we keep updating the density and also the displacement simultaneously. So this is a simultaneous scheme, which just like the building continuation nature in classic TO problems. In order to achieve the simultaneous approach, we have to parameterize our density, which is design variable, and also solution variable continuously with analytical function. So that function we use is a Gaussian process for each variable, which I will talk about later. With this continuous representation, what we can achieve is we do not really need the filter to solve some checkerboard issues, right? And also we can achieve super resolutions. So there are many advantages using a continuous representation of our variables. Okay, so this is our overall algorithm of our approach. So in order to do topology optimization, so we place the Gaussian process priors on all variables. The specific formulations of the Gaussian process prior will be given after these slides. And then we can formulate the general topology optimization problem by this objective function, which is integration of a local function. You can think about this as a compliance minimization, where here L0 represents the local compliance value. And this objective function should subject to several sets of constraints. C1 here represents the volume fraction constraints. Ci represent design constraint. For example, if you want to put a hole in your design domain, it is constrained by the Ci constraint. R here represents the residual constraint, where we have both the governing physics residual, the PDE residual, and also the residual from the boundary conditions. So we can use a penalty method to transform the constrained optimization into the unconstrained optimization by introducing these weight factors. And so that with this continuous representation and unconstrained optimization, we can solve this problem by estimating the parameters to minimize this total objective function. Okay. So yeah, if you have any question, you can stop me and ask. And yes, so as I just mentioned earlier, we place the GP priors on all the solution and the design variables. So why do we really need the GP priors? Well, the GP can provide a very powerful and probabilistic way for data emulation and also for function learning. So for data emulation, right? So basically GP leverages the data from the field. For example, if we want to learn the functions of the displacement, right? It's a continuous function, as I just mentioned. The data for that function is boundary conditions around the points close to the boundary where we know that, right? For example, if we fix the point on one of the edge, the displacement will be 0. Then we assume that the Gaussian priors on this we place the Gaussian prior on the displacement function, where it has a mean function m and also the covariance function. Both the mean and the covariance has its own parameters, theta and phi. So the covariance function we adopted here is a Gaussian type, where we have this exponential function captures the correlation between the 2 points in the design domain. And this correlation is regularized by a length scale parameter phi. And also we introduce this nugget parameter as the actual term to stabilize the training of this Gaussian process. So now we have defined our Gaussian process. We can estimate our function values at any given point in the design domain by these prediction formulations. So here we want to predict the displacement field, ith displacement component at the point x star equal to the mean function plus this correction term. So the correction term contains two components. The V here is a weight matrix, which contains the inverse of the covariance matrix. And also R here is the residual term. Here you can easily verify that by choosing x star equal to the upper letter x, the prediction of the UI reproduce the boundary condition data. So this reproducibility is very useful to capture the boundary conditions without using like residual terms from our physics-informed machine learning framework. Also, here we introduce the nugget parameter so that when we do the inversion of the matrix, covariance matrix, it can make sure that the invertibility is always satisfied and this matrix is always positive definite with this nugget parameter. Okay, so now we have defined the Gaussian process, right? We only just described the covariance function, but for the mean function, what we use is a neural network. So we place a neural network such as a multi-layer perceptron as a mean function. And here is a schematic of our framework to solve the PDE system. Yeah, before we actually solve the topology optimizations, we want to first to be able to satisfy our governing equations, which is very critical in TO. Here we have this neural network as a mean function, and we condition the output of the mean function with the prediction formulation from the GP. So eta here represent the conditioned output from the neural network. Here, from our prediction formulation, eta automatically satisfy the boundary conditions. Then we can further construct our physics-informed laws based on the PDE system. And then we can update the parameters in the neural network to minimize this PDE loss so that we can satisfy the physics. So our approach is, I want to mention that our approach is mesh-free because we use the collocation points in the design domain as the input of the neural network, and then we output the solution variables from the neural network at those collocation points. So during the training of our neural network, we do not really change the kernel parameter phi. Why? Because we already fix the parameter, and also we choose the parameter before the training, so that it can significantly increase the computational stability and also decrease the computational cost. So this choice does not influence the accuracy of our PDE solutions by this method. And if you are interested, you can read our paper with more details. And I'm going to show you the capability of this physics-informed Gaussian process by solving 3 different PDEs: Burger's equation, elliptical equation, and also another type of PDE system. We compare our framework with the conventional PINN. And we found that the absolute error is much smaller than traditional physics-informed neural network. So it's much better in terms of accuracy. Because the reason is because we do not have like a residual term for boundary conditions. All we have is to focus on minimizing the PDE residue, so it can be quite efficient. Okay, now we can solve the PDEs, and what we want to is really use this physics-informed Gaussian process to do topology optimization. However, a multi-layer perceptron neural network cannot really do the job because it has some issues such as spectrum bias issue, where only we cannot really capture these high gradients in our solutions. To better parameterize the mean functions, what we choose is PGCAN as our mean function. So PGCAN has 3 major components: feature convolution based on the 2D convolution neural network, where we define a feature space in the design domain. So the feature space has a parameter called the res parameter we define, which quantifies the resolution of the grid in the design domain, in the feature design domain. So if we can adapt the res parameter to adapt the topologies, which I will show you later. So after the convolution, we will interpolate the convolved feature onto the interpolation point or the collocation point to actually estimate our loss functions. So this interpolated feature will pass through the decoder to get the output of the mean function. So similarly, we conditioned this output of the mean function with GP formulation to get actual physical term, such as a displacement and a design variable. And based on those actual physics displacement and the design variable, we can construct our physics-informed loss. Here, in our compliance minimization, we have three different loss. LC is a compliance objective. LP here is a potential energy functional, which can be minimized to get the force balance condition. So where we can minimize LP to estimate the displacement field. And C1 squared is the volume fraction constraint. So before I do TO, I will show you how the solutions of our solution using our physics-informed Gaussian process for a boundary value problem. Here, this is a problem where we have a cantilever beam of the hole at the center. So the beam has applied external force on the bottom right corner. So we have the stress distribution on the top of the top row. And from the PG can we get the distribution of the error for the three stress distributions. And also we get the error from the multi-layer perceptions. And you can see here at the stress localization regions, we have pretty large errors from the multi-layer perception. And for PGCAM, we can get very high fidelity results compared with the finite element method. So this is a very critical aspect. We can be successful in compliance minimization for solid because we can really capture these local features using PGCAM. So, and also literature people use modified neural networks such as Siren to achieve similar results. But I believe our PGCAM method is much better. We can get this convergence done in about 200 or 300 iterations. So now here's the summary of my framework, where we place the GP priors for both the displacement and the density. Those are the formulations. We have these GPs, independent GPs for each variable, so that we can make sure that our computational cost is low with independent GP. And so we have three different loss components, and we use a penalty method to transform the constrained optimization into unconstrained ones. And what we do is just optimize the parameters for the neural network to minimize this objective function so that we can solve this TO problem. In order to effectively or efficiently estimate the loss function, we can use automatic differentiation method, which to get the gradient, right? Because we have the stress and the strain in our loss functions, which is a gradient of the displacement. However, automatic differentiation can be very expensive. What we use here is we use a finite difference method where we place a structured grid collocation points in the design domain, and the numerical gradient can be easily estimated. Also, to further stabilize our training process, we designed this curriculum training scheme where instead of directly targeting to a very low volume fraction targets, we gradually schedule our learning from a high volume fraction down to the target value. So this will significantly improve the stability of our training. So now I just introduced you with my framework, and let's just look at some examples. I will use 5 different benchmark examples. Those examples are quite available, and you can see them everywhere from educational papers for TO. And here, this one shows the video of the MBB example. We can see that at the early stage, we get this nice topology distributions, and later the algorithm just remove the gray areas. And here's another example showing the uniform loaded beam, where you can see the solid region gradually shrinking, right? That's because we are scheduling the volume fraction from a large value down to the target, and it gradually remove the material. We also compared our physics-informed Gaussian process framework with the results from the SIMP method. And we can get pretty good comparisons with the traditional SIMP method. And we can, as I just mentioned earlier, by changing the rest parameter, we can adapt the complexity of the structure. So what does the complexity mean? So the complexity we defined here is how much features in the design domain. For example, in this MBB example, the green pixel represents the interface between the solid and the void. So we define the complexity as a ratio of the green pixel over the solid pixel. So the higher the ratio, the more complex the structure, right? So this figure shows our approach where we can increase the rest parameter from 18 to 54. So the rest parameter is defines the resolution of our PGCAN, right? PGCAN grid. So by increasing the rest parameter, we can increase the complexity, which also represented by this statistical curve, static bar plots. However, you can also see from the plot that our approach has a pretty wide distributions of this complexity matrix. And this is because still, even we have a curriculum training schedule, we still get some instability happening during our training for some initializations. So we repeat our simulations or training for 10 different initializations, and for several of them, we see these outliers on the compliance and as well as some outliers in the interface fraction. Those outlier cases corresponding to these less preferable design structures, right? So with very high objective functions. So this is due to the instabilities. And we will solve this issue later using the shape functions, which I will mention in the next slide. And also we can compare the topologies from using the MLP as a mean function versus the PGCAN as a mean function. You can see the PGCAN can be very effective in remove the gray area and to get the nice structure binary distributions, right? Okay, so we can also use our physical informed Gaussian process approach for the fluid flow optimization. Here we are trying to minimize the energy dissipation by defining this function in the fluid field. And we compared our framework results with traditional solver such as a COMSOL, and we found that our framework can be more consistent and more symmetric in getting the topologies than the COMSOL approach. So it's a very effective framework. If you are interested in our approach and want to try the code, yeah, those code are all available in the paper, and you can download the paper from here and just give it a try. So it's very straightforward to implement using our code. Okay, so now I have presented is complex minimization, right? So the complex minimization is very simple TO problems for single material and a single physics. Single physics, I mean, is just a mechanical field. And it has some stability issues, as just showed you before, that some less preferable configuration shows up, probably due to the finite difference method. So one question we can ask, can we really extend this framework to more advanced TO problem? Yes. And I will talk about the more advanced topics, such as multi-material and multi-physics topology optimization, still using our framework, but with some modifications. First, we want to formulate our multi-physics and multi-material problem. So here, we want to use a thermomechanical problem as an example, where our objective function depends on the displacement field, which is a mechanical field, the temperature as another physics, right? And then we have the design variable as a density. So this objective is subject to several constraints, such as the constraint from the mechanics, which we have to minimize the potential energy of the displacement fields. And also we have to minimize the potential energy for the temperature field to get the correct temperature distributions. And also our design constraint should satisfy the mass constraint or the cost constraint, just similar with the volume fraction constraint in the complex minimization. So here for multi-material optimization, for multi-material design, the variable density is not a scalar. It becomes a vector with several components. So the rho zero correspond to the void phase, and the row 1, 2, 3, 4 corresponding to different candidate materials. Also, just like the simple method, we penalize our properties such as Young's modulus, conductivity, thermal expansion, and thermal source using this density field. One thing I want to highlight is the two design variables here in thermomechanical problem. We have U depends on rho, and also temperature also depends on rho. Those dependencies are implicit, so we have to capture this implicit dependency by in our sensitivity analysis. Okay, so to do the sensitivity analysis, basically we have to calculate the gradient of our objective function with respect to the design variables. So we use the adjoint method where we augment this objective function using adjoint displacement and also adjoint temperature field with their corresponding physics. So by taking the gradients of augmented objective function with respect to the density, and then you can organize the terms to eliminate some unknown gradients, such as gradient of U with respect to rho and gradient of T with respect to rho. We can get sensitivity formulations for different types of problem. So as I just presented before, so for complex minimization, it's a self-adjoint where we do not need to solve for the displacement fields in order to get the correct sensitivity expressions. Similarly, for the heat sink optimization, we also do not really need to solve for the adjoint temperature field. So for non-self-adjoint problems, such as a compliant mechanism design, the sensitivity expression is given here with both the mechanical and the thermal adjoint field. So those are quite different complex sensitivity expressions. So in order to get the estimate the adjoint displacement and adjoint temperature field, we have to simultaneously solve for these two set of partial differential equations. So if you are interested, I will not show my detailed derivation here, but if you are interested, you can look at our paper coming out soon about this problem. So yeah, so in order to do to summarize, in order to do multiphysics and non-self-adjoint non-self-adjoint TO problem, we have to solve independently the adjoint field by constructing these physical PDEs. Okay, so now here is our extended model. We continue to use PGCAN as our mean function for Gaussian process because the PGCAN is really good at capture the localization features. And we have PGCAN for the primary field, such as displacement and temperature, and also PGCAN for the adjoint field for displacement and also temperature. And also we have a dedicated PGCAN network for the design variable. And here we have more physically informed laws constructed from the conditioned outputs from the GP that automatically satisfy boundary conditions. And by these physically informed laws, we can learn these parameters for each PGCAN so that we can get the correct design of our topologies. So here is a summary of our extended formulations. We have 5 independent GPs where for each variable to be solved, and each independent GP will correspond to a specific set of partial differential equations, except for the density field, where we can use the density, we can use the GP for the density to make the prediction of our topologies. And similarly, we penalize all these physically informed loss function from a constrained problem into an unconstrained optimization using these penalization method equations. Okay, I want to also mention that the solution of all the primary and adjoint variables as well as density updates are all simultaneous because we define the GP as a continuous function for all these quantities. And as I just mentioned earlier, finite difference may not be accurate because it's only first order and it has some error at the boundaries. So instead of doing the finite difference, we borrow the idea from the finite element method where we use the shape function. Here, this shape function shows the quadrilateral element from finite element mesh. And then we can use numerical differential techniques such as defining B matrix, or the gradient matrix for estimating the strain, and also the gradient matrix to estimate the gradient of temperature. And then we can further use the Gaussian integration scheme from the finite element integration, right, to estimate the functional value at the integration points. So as we all do computational mechanics, those are very familiar to us. And I want to highlight that even though we use a shape function idea, but we do not really have finite elements in our approach, because our approach minimize the potential energy such that we search a continuous functions, right? So we search the parameters for the continuous function rather than getting just a discrete representation using finite element. And also during our training of the neural network, we use a dynamic collocation point scheme, which means that we train the network by varying the density of the grid in the collocation points. This will mitigate the issues such as overfitting issues. So yeah, this method has been demonstrated to be faster convergence, and we can leverage the whole library from the finite element about the shape functions, which can be very powerful for our TO design. So to demonstrate our multi-material capabilities, we first show the results for the five benchmark examples for both 2D and the 3D. Here, those also benchmark examples you can find in the literature, right? And we choose three different artificial material 1, 2, and 3. The parameters are given in this table. Material 3 has the lowest densities, right? And here we compare our physics-informed Gaussian process approach with approach from the literature, such as ordered sample approach and also the polymath approach. Those approaches are all available online, and we apply the three different constraints, such as the mass constraint, the cost constraint, and the combined constraints from the mass and the cost. Our approach can achieve pretty similar results compared with other established methods. However, we found that for the ordered sample approach, under the cost constraint, it gives the incorrect results. It should be all the red material in the design domain, just like what we found using the polymath approach and also our approach. So, and also our physically informed Gaussian process can produce very sharp and also very smooth surfaces. And this means that our approach can be super resolution compared with finite element-based method. Here, this figure shows the two design for the 3D compliance minimization using our extended approach, where we found at the false localized regions, we have the strongest material. And at some regions with like less stress localizations, we use a soft material. So, and this figure we shows the evolution of the objective function and also in conjunction with topologies. So at the beginning, a very early stage, the topology just emerged, and then gradually it evolved into the final stage with binary designs. So that means our training process is much stable. There's no large vibrations in the design domains. And also we can do similar with compliance minimization. We can do heat sink optimization for multi-material. Here, this first row shows the single material design, and the second row shows the three material design. And our method can be very consistent with the conventional method from the sink. And also I want to highlight that our approach is very easy to implement, because I just did this example in one day, and I got this result. So it's just very easy to implement and very friendly for new beginners. Okay, so as I just mentioned earlier, we replace the finite difference with a shift function, and we can get quite consistent result. For the finite difference, we show the distribution of the interface fraction versus the compliance by simulating 100 different initializations. The shift function has very narrow distribution, so that means the results are very consistent. However, for the finite difference, it has like 10% of the cases are outliers where the designs are not good and with rough surface. Those are the instability issues related to the finite difference method. So all the compliance minimization and the heat sink optimization are self-adjoint, which means we do not really need to solve adjoint variables. Here I present the examples of compliant device design where we have to solve for the adjoint displacement field because we need to construct the sensitivity for the objective function. Our objective is to maximize the displacement at the output point along these red arrow directions. So we can do like one material design and also the three material design. So our structure is very smooth and continuous with very sharp interface and a smooth surface, which is quite consistent and comparable to what we can achieve from the literature using finite element methods. And finally, yes, I will show you the thermomechanical design problem where I use the thermal actuator and the thermal gripper as the example. So this is a schematic of the design domains where we apply the high temperature field on the left edge. So the initial temperature in the design domain is 20 degrees C, and the high temperature on the left edge is 400 degrees C. Right? We are trying to maximize the output displacement on the right corner. So as an actuator and also as a thermal-driven gripper. So based on my sensitivity analysis, this is the analytical formulation for the sensitivity where we should construct our objective function based on this sensitivity expressions. We are using 5 different candidate material from the real world: nickel, steel, aluminum, copper, and titanium, which are summarized here in this table. So here shows the thermal gripper design, where this one shows the topologies where we get this smooth surface and very consistent results from my simulations. Simultaneously, we solve for the displacement field and adjoint displacement field, temperature and adjoint temperature. So those 4 different fields are solved simultaneously from our framework by different PGCAM with GPs. Now we can also compare the multi-material cases for the 2 example, and I show you 3 different repetition runs. And for the single material, we use the nickel, and the design for the actuator is given like this, and I would say, and I tell you that this is consistent with what we have in the literature based on the finite elements. And also, we have 3 material design where the green material is aluminum. So the aluminum is more preferable here for both the actuator and the gripper because it has lower density. It has much lower density compared with copper and steel, and also it has pretty high thermal expansion coefficient. If we replace aluminum with titanium, the titanium has very low thermal expansion coefficients and higher density. So in that case, the solution do not prefer the titanium. It just choose the copper and the steel, right? Similarly for the gripper design. So basically, this tells us our approach is physically interpretable, right? How we are going to choose the material is dependent on the physical properties of the materials. And finally, yes, I will present the preliminary cost analysis because we call it preliminary because there's no public available code that we can use to do a rigorous comparison using GPU or multiple CPU in parallel. So this figure shows the computation time of our approach versus the traditional simple approach. So at the low resolution or the finite element mesh, the simple method can be very efficient and it takes a very short amount of time to get the optimization. However, when we increase the mesh resolutions, our approach gradually outcompete the simple method. And we have to admit that the number of float operations is much higher using machine learning approach compared with finite element-based approach, such as SIMP. And the majority of the time is spent on the backward pass. So we have forward pass to estimate the objective values and the backward pass to update the parameters. So most of the time is spent on the backward. And in the future, we hope that we can have more rigorous comparisons of GPU accelerated simple method with our method. And also we are hoping that our framework can be more computational efficient for the nonlinear problems such as hyperelasticity and plasticity in the constraint models. And another thing I want to mention that even without the filter in our framework, we can still get consistent results across different mesh size compared with SIMP, where you have to adapt the mesh filter size to the mesh size to get consistent results. Okay, so here's my last slide. Thank you for your listening. And here we developed the physics-informed Gaussian process framework for TO problems. We can do advanced TO. So first, our approach is mesh-free and simultaneous. We use the Gaussian process to naturally satisfy the boundary conditions and also design constraints. And we use the PGCAN as our neural network architecture so that we can capture the local features. Our framework can handle both self-adjoint and non-self-adjoint problems, which means that our framework is designed for the general TO problems, not just for compliance minimization. And also we can easily implement the multi-material and multi-physics optimization by defining independent GPs for each state variables and also the design variables. With that, I will stop and thanks for my collaborations and also my supervisor, Professor Rami, and also the funding agencies. So with that, I will stop and thank you for listening. If you have any questions, you can ask me. Thank you. Yeah.
Thank you so much for your great talk. Now we have plenty of time for the questions. Feel free to ask.
Okay.
For me, I have a questions. I see you using the Gaussian process. Do you decide the prior randomly, or you pick some prior by choosing some particular values? And also, does those prior would change itself during the calibration?
You mean, so we choose the, sorry, I can't go to the slides. Yes, here we define the Gaussian process for each design variable and a state variable, right? And we do not really change the parameters for the kernel parameter for the Gaussian process. What we only update is the mean function parameter for the in the neural network. So before we train the neural network, we fix that Gaussian process parameter by estimating the MLE, or we just heuristically choose the hyperparameters for the Gaussian process. The reason we do that is because we can really ensure that our approach is stable, because we do not have to, for each iteration during the training of the neural network, we do not really invert the covariance matrix. We just store this inverse covariance matrix and we can use it during the training. Right, so that makes the training very stable and also reduce the computational cost.
Thank you. And does the initial guess of this mean value of those parameters would influence the efficiency?
I would say no, because we fix so for during the evaluation of the Gaussian process parameters, we fix mean function parameter, right? So, and we found that this evaluation does not influence the results or accuracy of our solutions or the PDEs. So, with more details, you can go to the papers and uh, yes, it does not influence the performance of the physics of our framework to get the accurate solutions.
I see, thanks. The
Okay.
result looks very impressive.
Yeah, we are not really using the probabilistic function of the GP. What we use is we just use the prediction formulations, right? So we just want to reproduce, we just choose the parameter of phi, right? Such that we can always reproduce the boundary condition data, no matter what collocation points we are using. We always reproduce this data from the boundary. So there's a large range of the parameter we can choose before the training. Yeah.
Thanks. And I also have several general questions. For the audience, feel free to break me if you have any questions you want to discuss with Alex. What motivated you to apply the machine learning approach to this field?
Well, I think, yeah, the short answer is machine learning research is a hot topic, right? So, and the topology optimization is basically in sitting at the intersection between between computational mechanics and also the structural design. So, and the machine learning provides a powerful tool for optimizations. So that's why I want focus on the machine learning based TO, really to see if we can improve the performance of the optimization, and also we can provide a better way for a general, more advanced topics such as multi-material and multi-physics, or maybe in the future, nonlinear material response into the TO problem. Yeah.
Yes, I think we are witness the different breakthroughs by those AI for science approaches.
Yes,
And
there's so
yeah.
many coming out these days. Yeah.
Yeah, from my uh, previous knowledge, I know that you are doing some experimental mechanics during your PhD studies, and then you switch to the modeling or the simulations during your postdoctoral studies. How do you feel about the shift during this process?
Well, I think the shift, there's definitely a shift, but it's not that so dramatic, because the advantage of machine learning, I would say that we have so many public available resources, and the code, people are sharing their code, and you can learn from their method and also from their paper. So it's not that steep learning curve. And also during my PhD, everyone should not just me, but maybe I guess everyone has courses like related to machine learning or computer coding, right? So this can be very helpful to these transitions. And also, most importantly, I have my colleagues and friends who are already working on the machine learning stuff, and they are very helpful to support my work at UC.
Great. How do you feel to be a postdoc at UC Irvine?
I think, yeah, this university, I have very little idea before I came here, but this school is very nice and great. So especially the weather, the South California weather is so nice, and also, my colleagues and friends, they are super hardworking, which is very surprising. And under such atmosphere, it motivates me to be also hardworking and to be productive. Yeah, this is really important. Yeah.
Yes, happy to see your smile when you mention
Yeah.
them.
Okay.
Yeah, in your views, what do you think are the key difference between doing research as a postdoc compared to a PhD student?
Uh, well, I think there's no fundamental difference between a postdoc research and a PhD research. You just work hard, right, to get the job done. That's basically what you have to do. But I think as a postdoc, I have to think about how to advertise my work. and how to let my work to be more impactful to a broader audience. That's one thing. And also I have, as a postdoc, I have to think about how to mentor the young students or maybe PhD students, and also how to build my research career that has broader impact. Also, that has some national importance, which aligns with objective from the funding acquisition purposes. So these are different mindsets. Yeah, I do have opportunities here as a postdoc to, writing a research proposal. I think that's helpful to build my skills, in the future as a faculty.
Yes, good luck with your futures. And
Sorry. Yeah.
do you have any advice to offer to the current or the aspiring graduate student in computational mechanics?
Yeah, just maybe open your mind because I'm doing experimental mechanics and then I transfer to machine learning and computational mechanics. Yeah, just be an open mind person to open the collaborations with as many people as you can. Yeah. Okay.
Thank you so much for your
Thank
sharing,
you.
Alex.
Thank you,
Does
Yang, for
anyone
the
else also has
invitation.
any questions? We still have a lot of time. Well, at the end, uh, thank you so much for giving us such a great presentations, and we will send you a gift later.
Okay, great. Thank you, Yang, for your invitation. Yeah, if you have any questions or anyone or you have questions, just email me and I'm happy to answer any questions. Or if you want to implement my code, and I have some problems, I can help you through that. Yeah, just let me know. Yeah, this is my email.
Yeah, and this video will be later uploaded to our YouTube channels, and we will keep updating the news in our website. And thanks for everyone for attending these seminars. Wish you have a happy Christmas holidays. Bye.
Bye. Bye.